Hi everybody. Our topic for this session is about per unit calculations. Now the primary advantage of using per unit calculation is that it greatly simplifies our calculation since all impedances of a given equivalent circuit can be directly added together regardless of system voltages. Now, please take note our power system consists of several voltage levels. From the generator, it's 13.8, and then the voltage is stepped up to 138 kV in the transmission lines, and then at the end of the transmission line, the voltage is stepped down to 69 kV for distribution to the customers, and then from 69 kV down to 13.8 kV for the distribution of uh, electric cooperatives or electric utilities. So these different voltage levels, since in each voltage level it is a separate circuit, so it would be very difficult to analyze power system if we have to consider the different voltages. So the tool that is being devised to address this issue of difficulty in encountering several voltage levels is to use the per unit calculations. The per unit calculation is simply getting or transforming the actual values of the parameters of the circuit now uh, based on a certain reference value, which we call as the base value. The first step is to choose base apparent power, or is base or is B. This can be in the form of KBE base or MBE base. So that means throughout the calculations, the common base for apparent power is or must be the same. Usually the common MBA base chosen is 100 MBA. Then after choosing the base MBA, we choose the circuit nominal voltages as the base voltages. So for every voltage level in the network, the voltage level at any point is the nominal voltage on that part of the network. Now the other base quantities like base currents, base impedance, etc. Shall be computed and not arbitrarily chosen. So take note that we have only the liberty of choosing the common MBA base and the nominal or the base voltages based on the nominal voltage levels of the network. But for the base current and for the base impedance, it should not be arbitrarily chosen, but it should be computed based on the common MBA and the base voltage. So for the single phase circuits, our base current would just be equal to the S base, divided by the base voltage B sub B. Now, where SB here can be KBA or MBA, depending on our choice now for the common apparent power base. And for our base impedance C sub B, impedance is voltage over the current. So for the base impedance, we divide the base voltage by the base current. Now since the base current here is equal to SB over B sub B, then substituting it here, so we just have B sub B squared over SB. So we have another way of computing for the S base if we do not want to use this. So we have to use this. Or we can use since most often in power networks our voltage levels are in terms of kV, so we can use the base kV and then square that, okay, divided by, okay, the S base is usually MVA, so we have the MVA base. So this is also the most commonly used formula for computing the S base. Now the per unit quantities are therefore the per unit current, okay, would be the actual current divided by the base current, and the base voltage, it would be equal to the actual voltage divided by the base voltage. And the per unit value of an impedance is equal to the actual value of the impedance divided by the base value of the impedance. And substituting the base impedance, so it's equal to Z actual times, okay, SB over B squared, no? Or Z actual in terms of MVA and kV squared, so it is this. And our kVA PU will just be equal to kVA actual divided by the kVA base. And our MVA PU will be equal to MVA actual divided by MVA base. Now, since our impedance has two components, no, the resistance and the reactance, okay, now we do not need to compute for the base resistance nor the base reactance. Okay, what we do is, okay, we still use the base impedance Z. So if this is our Z, then we divide both sides by the base impedance. So at the left we have here a ZPU, and then our R over Z base will just be equal to RPU, and our X over Z base would be equal to XPU. So we do not have to worry about the base resistance and the base reactance because we can use the base impedance. Find the per unit value. Similarly, our apparent power S is equal to the real power plus the reactive power. And we have chosen, okay, the base reactive power, or yeah. So we divide both sides, so we have S over the base apparent power equal to P over SB, okay, plus JQ over SB. So in other words, we do not need also to compute for the base power nor the base reactive power Q. It's enough that we have already the S base. So S over the S base is our SPU, and P over SB is our PPU, and Q over SB is our QPU. And drawing these components in as a phasor, so we have here the power, real power PPU, and our QPU is vertical, and then the hypotenuse will be our apparent power in per unit, and we have here the angle of theta. So from trigonometric functions, our PPU here would just be equal to SPU times the cosine of this angle, while our QPU would be equal to SPU, okay, times the sine of this angle, sine theta. Or our PPU can be also expressed as, okay, BPU, IPU, since our SPU, or apparent power per unit, is equal to the voltage per unit times the current per unit, and then we have cosine theta. And for the QPU, we can also express this as BPU, okay, times IPU, okay, times sine theta. So this is our common formula for a single phase power, where we multiply the voltage and the current and the cosine of the angle between this voltage and this current. Alternately, in phasors, we can write our apparent power as equal to the voltage times the conjugate of the current, no, I asterisk. So our apparent power S has a magnitude of S at a certain angle phi, and our voltage, phasor voltage, has a magnitude V and say an angle of theta V. And our current I has also a magnitude of I and an angle of theta I. Since this is conjugate, so the angle of I becomes negative. And so when we divide both sides by the apparent base, so at the left we just have SPU with this same angle phi, and then voltage divided by the base voltage, so we have BPU with the same voltage theta V, and I over IB is IPU, which has an angle of minus theta I. So this is how we can also express our apparent power per unit in terms of the voltage per unit and the current, okay, per unit. And now, change of base. Now, usually the per unit value of the reactance of our generator or transformers are based on their MVA capacity and their rated voltage. So, for each generator or a transformer, okay, it has a certain per unit value, and we call that as the given per unit, no, based on its MVA rating and the voltage rating. And so it is actually, it's a ZPU per unit is actually equal to its Z actual times this, now the ratio of the MVA base or its MVA capacity to the square of its voltage rating. Now, since we are talking about a power network where we have several voltage levels, then we need to change the per unit values of these generators and transformers to a new value such that we use the common MVA base. So in this case, if the chosen MVA base is different from their MVA ratings, and also or usually the voltage of the generator and the transformers remain the same. So in effect, when we use a new value of MVA, we still have its per unit value new equal to the Z actual, okay, times the MVA base new divided by its base voltage squared. So in this case, we can divide this this one and this a new equation, okay, by the given equation. So we have ZPU new divided by ZPU given, okay, and then we transpose the ZPU given to the right, so it's here. And then at the right, so we divide this by this one. So for the numerator, we have the MVA base new here, and the MVA base given would be down here. Whereas the KB base new is still down, and this KB base given would be up, and since they are squared, so we can divide first, okay, the two, and then square the result. So this is our formula for finding the new per unit value of the impedance, okay, with the given per unit value of that impedance, okay, times the ratio of the new MVA base, okay, to the old or given MVA base or the capacity rating of the generator or transformer, and then times, okay, the square of the given base voltage, okay, over the new base voltage. For the three-phase circuits, okay, we compute the base current per phase as I base is equal to apparent base per phase divided by the base voltage per phase. So the apparent power per phase is just 1/3 of the three-phase apparent power, whereas okay, the base voltage single phase is equal to the line to line base voltage divided by square root of 3. And simplifying, we just have 3 phase is base divided by square root of 3 times the voltage base line to line. Now for the base impedance, Z sub B would just be equal to the base voltage line to neutral. So this is per phase divided by the base current. Now our base voltage line to neutral is just equal to the line to line voltage divided by square root of 3 divided by I base, which is okay, from here it's equal to the 3 phase apparent power base divided by square root of 3 times the base voltage, okay, line to line. And okay, this voltage line to line will go up, so we have, okay, base voltage line to line squared, and then square root of 3 will just cancel, and then in the denominator we just have the 3 phase is base. So finally our is base can also be computed as the base kV voltage line to line squared divided by the 3 phase MVA base, because we have K equal to 10 cube, and then you squaring that, we have 10 to the 6, and our M here is 10 to the 6, so it will just cancel. So we have B squared and we have BA below. So one of the V's will cancel, so we have V up remaining, and we have amperes below, so it's impedance. Our three-phase apparent power is equal to square root of 3 times the line-to-line voltage times the line current. Now, if we divide this by the base apparent power, three-phase, so which is equal to square root of 3 times the base voltage times the base current. So at the left, we have, okay, is PO, and then square root of 3 just cancels, and line to line voltage over B sub base is our BPU, and I line over I base is IPU. So we have is PO equal to BPU times IPU. Also, our three-phase apparent power is equal to three-phase real power plus J, three-phase reactive power Q. So we divide both sides by the apparent base power. So at the left you have is PU, and then at the right we have, okay, P over is base is our PPU, and then Q over is base is our QPU. So this will be our another expression for our apparent power in terms of its components, okay, the real power per unit and the reactive power per unit. Now, if we draw the phase source, so we have, okay, power per unit, okay, as the horizontal component of the triangle, and then Q per unit is the vertical side, and then we have the hypotenuse as our is PU, okay, forming an angle of theta with, okay, the horizontal, or with respect to the power per unit. So using our trigonometry, our PPU will just be equal to the hypotenuse, which is PU times the cosine of theta. So we have this. And also for QPU, this would be equal to the hypotenuse is PU, okay, times the angle, the sine of the angle theta. So we have QPU equal to is PU, okay, sine theta. Now, also we are familiar with the formula of power as three-phase power as square root of 3 times the line-to-line voltage times the line current times the power factor. So when we divide this by the base apparent power, three-phase, so at the left we have power per unit, and then at the right, okay, square root of 3 just cancels, then line-to-line voltage over voltage base is BPU, and line current over I base is equal to IPU, okay, then we have the power factor. Now take note that this is for three-phase, and you notice that this is the same as the formula for power per unit in the single phase. So whether we have single phase power or three phase power, the per unit value, okay, has the same formula as this. Now similarly for the reactive power, okay, which we define as square root of 3 times the line to line voltage times the line current times the sine of the angle theta. So we divide this by the base apparent power. So we have QPU at the left, and then at the right, okay, this square root of 3 cancels, and line to line over voltage over visa base is our VPU, and then I line divided by I base is our IPU, and then we still have sine theta, which is also true for a single phase. So okay, for single phase and three phase reactive power per unit, okay, we just use, okay, this